So guys, thanks for coming to this semester's first virtual simulation lab seminar. Today we're going to have one on something new, fundamentals and applications of density functional theory, given by Astrid Martens. So Astrid, please.
Okay, thank you. Thank you for the introduction. I'm happy to see that there's so many people interested in learning about density functional theory, which is what I do every day. So, yeah, my name is Astrid. I'm a PhD candidate at Departments of Material Science and Engineering. So, the outline for this talk, I've divided into two parts. So, the first part of my talk, I will introduce you to the fundamentals of density functional theory. So, that involves solving the many-body Schrödinger equation, and we'll also move into DFT applied to crystalline solids, which I'm mostly concerned about. And the second part, we're actually going to talk a bit about how to do our DFT calculations. So when you go out here, you'll have some knowledge on how to actually sit on your own computer and run your calculations yourself. Yeah, so that involves a small introduction to the VASP software, which is what I use for these DFT calculations. Okay, so first off, what we're doing is computational materials science. That would be the field. So it's not like I'm coding some language or whatever. I'm a material scientist. So I also do experiments, but I just do it on a computer. So this is me sitting on my lab in my office doing my computer experiments. So DFT calculations, they're also called first principles calculations or ab initio. That means from the beginning. It just means that density functional theory calculations, the whole theory, it's not based on any, you don't need any empirical parameters into your theory. It's just plain and simple quantum mechanics building up the world, right? So you just set up your experiment and then let the computer apply the theory. And then you get out, or I get out, a lot of nice properties describing my material. So structural properties, vibrational properties, electronic, you name it, you can get it out. Okay, so part one, the fundamentals of DFT. I'll just start with a slide of some definitions so I don't sort of lose you when I get into the fundamental theory, so we're all on the same page. So just first, a wave function in quantum mechanics, that just describes the quantum state of a set of particles in an isolated system. So that's nicely illustrated here. You have a particle, and in quantum mechanics, you can just like make it into a wave, right? Okay, an operator. That's not a scary word. It's just it just does a mathematical operation on some variable. So you shouldn't be afraid of that word. Easy example is a derivative. That's an operator. When you go into the quantum mechanics, you deal with quantum mechanical operators. And in quantum mechanics, any observable, anything you can physically measure in quantum mechanics is represented by an operator. So for example, the kinetic energy. In quantum mechanics, the kinetic energy is written like something like this. So it's something, something, and then a derivative, right? So, and lastly, ground state, that's mainly what we're after. We're after defining the ground state of our system. That's basically the most stable state of our system, the system, like the energy, the lowest energy state, right? Okay, so that's that. So now we start from the beginning. So we're interested in finding the ground state of a set of particles. And the way we do that is we try to solve the many-body Schrödinger equation, right? So we have our wave function here, which describes our system of atoms or nuclei and electrons. And we have our Hamiltonian, which is an operator, an energy operator, which you apply to the wave function. So again, it's just an operator. It's just you can divide it into energy terms. The T operator is just taking care of the kinetic energy. And then you have the potential or Coulomb potential operator, which just includes all Coulomb interactions. So, you know, between two charges, you always have Coulomb interactions, right? So it's just, yeah. But you can see from this equation that from basic quantum mechanics, we only sort of we look at the single electron state, so because that's the most easy. Here we have a bunch of nuclei and a bunch of electrons, which makes this sort of a very complicated equation to solve. So let's try to make this at least a bit simpler. And the first thing we do, we apply the Born-Oppenheimer approximation. That approximation just basically says that the nuclei, they are big and they are heavy and they are slow. And electrons, they are small and they are fast. That means that you can decouple the dynamics of the nuclei and the electrons. So the time electrons need to find their ground state for one specific positions of the nuclei, it's much faster than the nuclei are able to move, right? So that means that the electrons, they only see this external potential of static nuclei, right? So we decouple the wave functions. That means that we from now on can only concentrate on first solving the ground state of the electrons for one fixed set of atomic positions. So, great. We reduced our number of variables a bit. And now the Hamiltonian only consists of terms which include electrons. So you have the kinetic energy term, and then you have the potential terms here. So the electrons interacting with the nuclei, which it only sees as an external potential, and then electron repulsions. But let's just pause a bit and think of how big of a problem this turns out, how fast this escalates in terms of dimensions of the problem. So, okay, real materials. Let's take an easy, small example. Let's look at the carbon dioxide. The carbon dioxide molecule consists of 22 electrons. Each electron are described by 3 spatial dimensions, coordinates. That means that solving the Schrödinger equation becomes a 66-dimensional problem. Okay? If you look at a nanocluster of lead, each lead consists of 82 electrons. So say that the nanocluster has 100 atoms. That means that the number of electrons in the system is 8,200, and multiply that with 3, and you have the dimensions of your problem. So you can see that solving the many-body Schrödinger equation is, for all practical materials, a bit of a hassle. Here is where we start to approach the density functional theory, right? So the electron density, that's actually a true observable, which in principle can be measured. That can be defined from the wave function. That reduces from 3n dimensions to 3 spatial dimensions. So the electron density is only 3-dimensional, right? So that seems to be sort of a hint, let's go in that direction. Let's try to solve the Schrödinger equation in terms of considering the electron density, right? Hint, hint. Now let's make another approximation. So consider the electron as a point charge in the field of all other electrons. That would simplify the many electron problem to many one electron problems. So you go from a situation like this to something that looks like this, and you consider single electron wave functions. You still would simultaneously need to know them all, of course, to now it's there, to calculate the one. But still, let's keep it there. So that means that we can now redefine our electron density in terms of all the single electron wave functions. Okay. So again, we're approaching now the heart of DFT. So the heart of DFT is based on 2 very fundamental theorems. And the first theorem states that the ground state energy is a unique functional of the electron density. So here's where the fancy word functional comes in. But it's not really a fancy or a scary word. It's something you've all done. So a functional is basically a function of a function. A functional you all would know. An integral, that's a function. A functional, sorry, right? So yeah, don't be afraid of the word functional. But the theorem basically states that the electron density is all you need in order to define your total ground state energy. So that's a really good thing. And the second theorem, that tells you how you're going to find your ground state density. Well, you just minimize your energy functional. So that just means moving down the well until you found your ground state density. And then you're there. So let's talk a bit about this energy functional. This energy functional can be divided into 2 main parts. The one that is known and the one that is unknown. So the known part is basically all the energy terms that we already seen, the kinetic energy, and then all the potential energy terms, which is connected just to the Coulomb interactions, right? And then we have the exchange correlation functional. That takes care of all the quantum mechanical interactions between electrons. And unfortunately, that's something that we don't really know. It exists, the perfect functional exists, but we don't know it. So in all calculations in DFT, this is something that needs to be approximated. So the simplest exchange correlation functionals that you will stumble upon in DFT, it's called the local density approximation. That's the LDA, only bases itself on local electron density. And then the generalized gradient approximation, which also takes into account the gradient of the electron density. And there's a lot of developments going on all the time on improving these exchange correlation functionals. But I'm not going to dwell anything more upon that now. So recall the 2 theorems. So Kuhn and then his postdoc Sham, they found out how you can actually find, like in practice, how you actually obtain the ground state electron density. And so they came up with this scheme. So the first thing you do is that you just consider this a set of single electron wave functions, and they're not interacting. So it's a non-interacting system. The interactions are sort of implicitly accounted for in these potentials. So the Hamiltonian for the single electron wave functions is the external potential, and then the Hartree potential, hence the H, which is just electron interacting with the electron density, and then this exchange correlation potential, which we have to approximate. So the self-consistency scheme, that's what we actually do in our calculations. The first thing we do, we just guess some electron density. And so we make a trial electron density. And we put that into our Hamiltonian here. And then we solve the Kuhn-Sham equations, which is this set of equations here. So one equation for each electron. And then we obtain a set of wave functions. And we already seen how this correlates with the electron density. So then we can recalculate the electron density. And if the electron density we got out was the same one as we guessed and put in, then we have a self-consistency in our loop. So that means that we obtain the true ground state. If it's not the same, then you replace your electron density, put it as a new trial, and then just loop through again. And so that's how you minimize. You search for the lowest, the ground state electron density by loop through this. So yeah, guess an electron density, put it in your Hamiltonian, then recalculate the electron density. If it's the same, perfect. Then you got out the same as you put in. So then we know how we obtain the electronic ground state, and now it's super easy to find the ionic ground state. So, or maybe not to find the ground state, but at least from when you know the Hamiltonian and you know the set of correct wave functions because you have the right density functional, right electron density, you can easily calculate forces on ions, and then you just move along the steepest descent of the ionic forces to obtain the ionic ground state. So in practice, you use an algorithm, you move it a bit, and then you recalculate the electronic ground state, and then you sort of always move it until you reach some sort of ground state for the ions as well. And when you obtain that, you can go even further and like move the ions a bit away from their equilibrium position. Then you can obtain Fourier constants and vibrational frequencies. Yeah, you can calculate the whole phonon spectrum for the ions. There's a lot of possibilities. Okay, so now we're moving into more specifics of crystalline solids. And now we're concerning with the plane wave DFT. So let's see what that is. Let's first define a crystal. So a crystal is a periodic arrangement of atoms. This crystal, so consider the nuclei, they have some positive charge, right? And they represent the periodic potential. Looks like this. A free electron is represented by a plane wave. This looks like this. But what happens if you put an electron in a crystal? How would the wave function look like? And this guy Bloch found out some nice things. It's basically, the result is Bloch waves. So you have the still plane wave, and it's just modulated by some random potential, which is also periodic with the lattice. So it's basically just perturbed free electrons. That's your answer. And here is where plane wave DFT sort of comes into the discussion. Okay, so I'll talk about some very important concepts in terms of your actual calculations in DFT, or plane wave DFT. The first one is cutoff energy. So a very central concept in DFT, or reciprocal space. Reciprocal space, mathematically, it's just the Fourier transform of your real lattice, where all the dimensions are turned upside down, basically. So everything which is large in real space turns small in reciprocal space, and vice versa. Small things in real space extend, far in reciprocal space. Okay, and then you might remember that from math, that if you have some periodic function, you can always expand it in terms of a Fourier series. So let's look at our block function, which is the electronic wave function in our crystal. So this was periodic with our lattice. So we expand it, and the wave vector turns out to be, or the, is there some sort of a timer? No, I don't know. Anyway, so the wave vector actually turns out to be some reciprocal lattice vector, right? And if you multiply this in here, you see that the block wave can be represented as a sum of plane waves, which has a wave vector of g plus k, right? And then you sum over an infinite number of reciprocal lattice vectors. The problem numerically is, of course, that you cannot deal with infinite sums. So in our calculations, we have to define some sort of cutoff. So each plane wave in this sum has a kinetic energy, which is given by this. So for a larger and larger reciprocal lattice vector, you have an increase in kinetic energy. So we just, in our calculations, we just define some cutoff. We don't consider plane waves which have a higher energy kinetically than this specific cutoff. So this is a really important input parameter for you when you do these calculations yourself. And I'll come back to how you actually choose this cutoff energy, because you have to do convergence testing in terms of your total energy to actually choose a high enough cutoff energy. Another important concept is K-point sampling. Again, we're in reciprocal space. You just have to have some sort of sense of what that is, but yeah, okay. So our wave vectors, our plane wave vectors, they span the reciprocal space. And in reciprocal space, the primitive unit cell is called the Brillouin zone, or the first Brillouin zone. Then you need to know that any K vector which extends the primitive cell in your reciprocal space, or extends the Brillouin zone, if it can be written as the sum here. So if it just differs by some reciprocal lattice vector g, it's basically the same wave, just sort of phase shifted, right? So that means that in terms of considering which plane wave vectors we need to look at, we can only consider the first Brillouin zone, and we sort of captured it all. So not dwelling too much on this either, it means that the math in DFT in terms of evaluating integrals in K-space means that you only integrate over your first Brillouin zone. So this is where the K points come in, because again, numerically, you can't do integrations. You have to do summations, right? So that's what you do. You just sample your Brillouin zone. You just put in some K points here, and then you evaluate your integrals by like summing up over these points somehow. Okay, so might be a bit vague, but this is also an important part of your calculations, that you have to define, you have to map your Brillouin zone in terms of K points. And the number of K points have to be sufficiently large so that you obtain reliable energies, right? And converged energies. Third important concept is the pseudo-potentials. So in terms of physical quantities like chemical bonding and other characteristics of the material which we care about are mainly characterized by the outer electrons, the valence electrons. So let's make life a bit easier for ourselves. So instead of considering, like when we minimize our electron energy, let's not consider them all. Let's only consider the outer electrons and just freeze in the inner electrons. That makes calculations so much easier to do, because the inner electrons here, they're just now like in this big, some effective positive potential, and then you only let this outer here move. And a nice thing is that current DFT code, they provide these pseudo-potentials. It's not like you recalculate what this inner thing here is every time. So there's often a library with these pseudo-potentials that you use for each element in the periodic system. Okay, so last concept before I move over to part 2. The calculations are performed with periodic boundary conditions. So it's not like you implement a very huge cell when you calculate some crystalline thing. You implement the unit cell, or you implement a supercell. And the cell you implement is just periodically repeated in calculations. So that means that there will be interactions across your periodic boundaries. So that means that you can model non-periodic entities like interfaces or like molecules or defects if you want, so impurities in your system. But then you have to take care when you actually define your supercell, because of these artificial interactions across the periodic boundary conditions. So for example, if you want to simulate a molecule, maybe first of all, maybe plane wave DFT is not the best thing because it's optimized for crystalline structures. But if you don't want interaction across the periodic boundary condition, you have to make a lot of blank space around it, right? And also when you simulate defects, you also need to take care on how you define your supercell to not have artificial interactions due to the periodic boundary conditions. Right, so that was a lot of concepts. Now we're actually going to talk a bit about how we actually do DFT calculations on our computer, some practical aspects. So the software we use is called VASP, or Vienna Ab Initio Simulation Package. So what is it? Well, it's one of the software packages that uses DFT. It uses periodic boundary conditions. It uses the pseudopotential method with a plane wave basis set. And yeah, it can model system. You can always model systems which are larger, but in terms of computational cost, is not really optimized for any, like, you don't model disorder in DFT. You don't implement the cell with tens of thousands of atoms, right? Doesn't make sense. Yeah, and it's a commercial software package. There are other DFT codes or packages which are used, Quantum Espresso, Abinitz, Siesta. I don't really have any knowledge about them, but there's a lot of people using the VASP software, and one main reason is, well, it's reasonably well documented, and also they have a large set of pseudopotentials which are very well tested. So that's perhaps one of the main things we pay for when we choose to use VASP. So doing simple DFT calculation in VASP includes inputting into your computer or making 4 main files. There are a lot of VASP files with, it's named something car. I don't know what the car comes from, so don't ask. Anyway, we have the in car, you know? Oh no. Okay, but don't care about the car. You have the in car, includes inputs. So that sort of defines your setup in terms of user-specified parameters. For example, global break condition, energy cutoff, degrees of freedom for the ions, and so on. And then you have the POS car, so that's the position car. It's where you define your periodic simulation cell, and yeah, it contains basically information regarding the geometry of the system. And then you have your POT car, or the potential car, and this car includes the pseudopotentials. So this is basically something that is provided by VASP, so it's a big library. And it also includes, information about the pseudopotential and the exchange functional. So you have to choose one. And then the K-points. So that's a file that specifies how you put out the K-points in your Brillouin zone. Right.
No car there, though.
It's no car. K-points car, it should be called. But I don't know. Okay, so let's just take a simple example. This is a simple perovskite. So in the perovskite world, this is a simple example. Barium titanate. Okay, so cubic barium titanate has A equals B equals C lattice parameters, and then you have can define some fractional ionic coordinates. So just there's not 8 barium that need to be defined. You define the 1 barium, right? And then the other ones are just like mapped out by the periodicity. So this is what you define, and that means that you can create your POSCAR file. That would look something like this. So what does it mean? Well, this is basically just the Cartesian lattice parameters. You have a scale factor here that you can choose to use if you want. You could, in principle here, since A equals B equals C, set the number of 4.01 there, and then just like 1, 0, 0, 0, blah, blah, blah. But yeah, never mind. So this specifies the elements, and here's number of each element. So the first one here belongs to barium, then the second belongs to titanium, and then we have the 3 oxygen. And this is just the fractional coordinates. So it's very Very simple. And then we have the INCAR file. This is a very simple INCAR file, and you can specify a lot of tags here. So I'll just mention the ones that I've put in, and you can always argue whether these are the most relevant ones or not. But never mind, just to have a feeling of what you put in there. So for example, you define the NCAT, that would be, sets the energy cutoff. That needs to be tested by convergence testing. I'll come back to that. Then you, for example, set the maximum of electronic steps. That's basically to prevent that the calculation never ends, so it has some sort of dropout if it, never converges. And you always set the convergence criterion both for ions and electrons. For ions, you can choose whether you want the convergence to be in terms of total or forces on each ion, or the total energy, convergence in total energy, and it also depends on how stable your system is initially. For example, if you have some vacancies in your system, it might be harder to relax it in terms of, it will always be some forces there, for example, if you have to have some artificial interface or whatever. You set the electronic convergence or the global break condition to an appropriate number. And then you also can define the degrees of freedom in your system. So for example, if you want the volume to change during your relaxation, or if you want to fix the volume and you want to only relax ions, or you don't want to relax the ions at all, you just want to look at the energy for one specific configuration of atoms, you set this. And you can also set the algorithm for how you update and move your ions, right? So there are different choices there. So this is basically a file when you set a lot of tags. K-points file, that's quite small file, doesn't contain a lot. I always use the automatic mesh. I can't really, there's a lot of ways. You can explicitly set the K-points in your Billois zone, and but I use always some automatic mesh, so my file looks simple. And the other things here is that I specify that I want to generate a gamma-centered mesh. So the gamma point, that's just denotes the central point in your reciprocal space. Nothing more fancy. And then just subdivisions of k-points along each of the reciprocal lattice vectors. And this is also a subject for convergence testing. POTCAR file. So in VASP, you get a big library so you have pseudo potentials for all the different elements in the periodic table. And so you just copy paste all your elements into your POTCAR file, and you get a big file basically. So it contains some stuff, for example, type of pseudo potential, because often or sometimes you can choose, never mind, type of pseudopotential, and here also the specific exchange correlation potential. And you can choose different pseudopotentials for the same element by changing the number of valence electrons, which are free to move, right? So this is one for barium. Yeah, it's a big file, contains a lot of stuff. So what do you get out? Some standard output files is you have the CONTCAR file. That basically looks the same as the POSCAR file. It's just your relaxed ions. OSSICAR file, one of the more important ones. It contains all your electronic and ionic steps. I'll show you this afterwards. And you have an OUTCAR file, which is just like complete output. So you go there if you want to see how the forces are, charges and ions, symmetry, etc., etc. And then you also get out a charge car. And you can, there's a lot of things you can get out, so I can't state them all until you go actually start doing these calculations yourself, but you get some sort of idea of what you put in and what you can get out, right? So the OSSICAR would look something like this. So we talked about the self-consistency scheme and the electronic iterations. That's basically what you see here. So for each lump here, that's a set of electronic minimation steps. And then you have defined some sort of electronic convergence step, so then it goes out of the loop and it calculates forces on ions, it moves forces on ions, and then it's just stars all over, right? So it calculates the total energy, and what you set as a break condition is actually when the energy difference into calculated total energies, when that becomes smaller than something, then it just breaks out a loop. So here it's something 10 to the minus 8 or something. It might be 7, since it's there. And then you get out a total energy. And so it will continue to do this until it reaches some sort of your criterion for the ionic relaxation, right? And so in the end of this file, you have the total energy of your relaxed ionic steps. Okay, so two things we talked about, the K-points, and we talked about the cutoff energy, and it's important to test convergence of that. You always have to do that when you implement some new material system in your calculations. You always have to do these convergence testing. So what you basically do is just you define, for example, a number of K-points, and then you just increase the number of K-points and then calculate the total energy. And when the total energy starts to converge, you choose that number of practically the smallest number of K-points that you need to make your calculations converge. And then you do the same thing for the cutoff energy. And also be aware that like the cutoff energy and the K-points, the number also influences structural parameters like the lattice parameters, which also we see would converge. Here is plotted against the K-points. You can make a point that total energies are not really what we care about in DFT. We always look at energy differences. It's not like, oh, the total energy of this system is minus 42. It would change with the pseudopotential and with all your choices. But if you keep your choices the same when you do different calculations, so keep the K-points and the cutoff energy constant, then you can compare energies, and that's relevant. And to have some sort of sense of the energy resolution in DFT, we often say that it's like a bit like approximately 1 millielectron per atom. So it's a bit hand-waving, but it's fine, is what we say. Okay, so I'm approaching the end.
That's perfect. That's excellent timing. The pizza just got here.
Yeah, great. So just a few slides about DFT, which you can consider as a theoretical microscope. That's a favorite phrase of my supervisor when he talks about DFT. So for a lab experimentalist, that would be, okay, so you can actually use it as a microscope. That's cool. So point is, with DFT, you can obtain structure beyond the current capabilities of experiments. And you can predict properties at a resolution and length scale currently inaccessible to experiments. But of course, it all goes hand in hand. I'll just give you a flavor of what I do myself. So I'm sort of in the business of thin film technology, if I flatter myself. But okay, so thin films is sort of like the big deal in terms of downscaling of electronics. So yeah, thin films is in mobiles, in whatever electronics. You obtain a thin film by growing it on a substrate. So that's what you see here. And a bit more detailed, see, a substrate and a thin film often have different lattice parameters, and then you have strain here, and well, then you can have some defects or impurities in your thin film. And so this guy here is struggling because, so this guy here is sitting in the lab and he's doing some measurements on his thin film and he doesn't know what he's measuring, right? So there's, okay, so the result of what I'm measuring, is that because I have strain in my film? Is that because I have some interface interactions going on? Is that because of defects? I don't know. So here is where DFT, the beautiful tool of DFT, comes in, because it's so pure, right? So, so this is me again. And what I do is that I also want to look at this thin film, but I want to isolate effects, and I can do that in my computer. I don't need a substrate, for example. So I want to look, okay, I want to look at the thin films, but I only want to look at the effect of strain, right? So I can just make a model, and I can impose that strain without having the substrate. So in DFT, you have complete control of degrees of freedom. That's a nice thing. So you know your model, so you know exactly what you measure. Of course, the challenge is, does the model correspond to reality? So I don't say that DFT should replace lab experiments. I say that they have to go hand in hand. And just a bit visual of the outputs you can actually get. So looking through the DFT microscope, there's a lot of nice visualization. It's not like I sit reading these files of numbers. I can visualize this very well to actually study the structure at an atomic level. I can, if I want, plot the charge densities. So I can see the charge density if I want. And I can visualize density of states and, you know, get the information I want about all the electronics and structural properties of my model. So I hope, in summary, that I've showed you that density functional theory is a powerful tool for predicting material properties, and also that doing the actual calculations is not so scary. And yeah, I have some references here. Two books about the fundamentals and your future Bible if you go into DFT using VASP. It's the VASP manual. So thank you.